So as you can see on the voltage regulator, right now we're outputting 1.20 volts, which is also displayed on our oscilloscope here. There's a little bit of variation. We're seeing 1.22 volts RMS on the oscilloscope, 1.20 on the voltage regulator. I've attempted to adjust the signal here, but it doesn't seem to have any response to that adjustment. Anyways, I do see that there's a bit of a drop in the voltage on the oscilloscope. It's very brief, but true RMS voltage, we're looking pretty good at 1.2 volts. We'll slowly begin to increase the voltage. You can see the voltage increasing on both the voltage regulator and the oscilloscope. One thing that I found interesting is once we get to right there, about close to 12 volts, which we're showing 11 on the oscilloscope, 11.5 on the voltage regulator. But once we get close to that 12 volts, our voltage signal on the oscilloscope just goes clean. It's flat. And I'm wondering if that's a result of we've got 110, 120 volt AC input going through a transformer. So it doesn't have to clean that signal as much. Although that is a 60 hertz signal coming in from the wall. I don't know, it's interesting. I'll go back down so we can see. So if we reduce the voltage, you can see almost like a square wave start to form again in the signal on the oscilloscope. I haven't really noticed that it gets any worse at a lower voltage. Kind of scale back up here. But then once we approach that 11 volts, it goes flat. We can increase up to 15 volts output, and I think our oscilloscope, our analog inputs are limited to 10 volts, so hopefully I haven't damaged anything, but the tool is limited to 10 volts input, so we can't really see this top end of the spectrum. Maybe that answers my question. Maybe that's why the line goes flat, because we can't measure RMS past 10 volts. The tool is protected from that peak-to-peak voltage, perhaps. I think that answers my question. So I'm going to use the multimeter here to just get a second opinion on the voltage coming from the voltage regulator. So you can see as I start to increase the voltage, we can see that on the multimeter. And at this upper limit, we're a little more accurate. The voltage showing on the display of the voltage regulator compared to the voltage shown on the multimeter. So all in all, this is a pretty neat project. I enjoyed the construction, and it's neat to be able to see all of the different components that go into transforming this AC voltage. So we'll do a quick high-level overview of the components that make this possible. Of course, we have our 120 volt input AC from the wall, which then goes through the transformer that you see here. The transformer steps that 120 volts down to 12 volts. 12 volt AC power would then make its way through these 4 diodes that you see, which create a bridge rectifier. These diodes essentially convert the AC power into a DC current. The large capacitor that we see here is an input filter. It basically takes some of the spikes out of that voltage that we would see. Mounted to the heat sink here in the back is an LM317 3-terminal adjustable regulator. The input from our potentiometer essentially changes the speed at which the regulator opens and closes, which modulates our output voltage. The second large capacitor that you see here is an output filter that helps to absorb any shock load that may be applied to the output circuits farther downstream.